Hello, CS2 students. Let's see if I can get this right in one take now. In case you couldn't tell by my voice, this is Scott. I'm either your tutor or I'm one of your tutors, and I'm making this video because I gave a lot of you some very bad advice with how to approach Prac 5. And if you took my advice, this would have resulted in you not having to engage with one of the key components of this prac. So I know that a lot of you are going to be working on this prac and submitting it later today. So I feel that it's important that I make this video for you to explain to you how to properly approach what we're going to be talking about. And then in light of that, I feel that it's fair that I ask you to submit your prac work, this prac 5, by 11 p.m. tonight. I cannot be more flexible on this, but I feel that it's fair. If you did indeed do the prac in the way in which I had explained to you, these changes that we're going to be talking about should not take you too much time. Yes, so that being said, I think let's get started. So here, as you can see, we've got a solution, and I have Professor Wells's tree class loaded up here. It's as it was. All I have done is made the additions of the replace right and replace left methods, excuse me, which you were required to add in question 1 of Prac 5. So yes, that shouldn't be too new to you. And then over in the program here, we have a very basic program just to illustrate what we're going to be talking about. Here I create a tree string. It contains it contains the nodes A, B, C, D, E, F, and G. Kind of created very explicitly here, but and then over here we have two tree strings, pos and parent, which we are going to use to point to the different nodes in my tree over here, this main tree that we'll be working with. And then over at the bottom here, I have some methods which I use to handle printing the tree to the console. And then over here in this line, I call that method. And then here is a read line to make sure that the program doesn't immediately terminate once it's finished executing. Okay, so from here, if we run this, we will see, I hope this is clear, that here is our tree. We have A as the root node, and then from A, in A's left subtree, we have B, which in B's left subtree, we have C, and in B's right subtree, we have D. So altogether, B, C, and D make up A's left subtree, and similarly, we have E within A's right subtree, with E's left subtree containing F and E's right subtree containing G. And so E, F, and G together make up A's right subtree. Here I have a similar picture. It's not quite the same tree from online. And so I hope you can see how these are the same, where here we have A as the root node, then B, C, and D in A's left subtree, and the letters are a bit mixed up here, but you can see how the right subtree is, I hope you can see how that is the same here, where we have A as the root node, then B, C, and D in the left subtree, and in this case, E, F, and G in the right subtree. Okay, so that's the program as it is. Let me close that, and let me close that. So, okay, maybe I should open this again. During this Prac 5, you would have come to a stage where you found yourself in a leaf node, and you want to change the data that is contained in that leaf node, or effectively change the data that is contained in that leaf node. Now, during the prac, a lot of you came to me and asked, how do I change the data that's contained in a node? There's no set data method in the tree class. And myself, having not properly read the memo, I guess, and kind of not second guessing myself, I said, that's weird that there's no set method in the tree class. So go ahead and add a set data method to the tree class. And so a lot of you did that, and in doing that, we've avoided dealing with the core issue there, which is, how do I effectively change the data contained in this node without actually directly changing the data that's contained in this node, i.e. without making any changes to our existing tree class? How can we accomplish this? Changing the data, sorry, my windows are a bit messed up. How can we accomplish this? Effectively changing the data in C. And the answer to this is that we are going to create an entirely new node which will contain the data which we want to insert in the place of C, and then we're going to replace node C with this new node that we create. So, or in this case, if we were looking at C, sorry, I don't think I explained that very well, but I hope you're following me. Okay, so let's just, for some clarification, let's get our pos, which we are going to use to point to the node of interest, in this case C. Let's set pos to point to C. So we'll do pos equals, it will be mytree dot left dot left, and that should be pointing to C now. If we run this, we will see that pos is now pointing to C. So in this case, what we are trying to achieve is we are trying to change the data contained in node C effectively. Okay, so how do we go about doing this? Well, there are two steps. We are going to create a new node containing the data which we wanted to contain in place of C, and then we are going to replace C with our new node. So this asks the question, how do we replace a node? Well, in question 1, we were told, or you were asked, to write or implement these two new replace left and replace right methods. But a problem arises here in that what these methods do is they only replace either the left subtree or the right subtree of the node which we're looking at. They do not actually replace the node which we're looking at itself, only its left or right subtree. So how do we go about replacing the node itself? Well, it's likely that this node is in fact a subtree of its parent node. And if you're familiar with trees, which you should be, I hope, you'll know that our node has no way of knowing which node its parent is. It contains no pointer to its parent. Yeah, I hope that makes sense. There's no field within the tree class which is a parent pointer. So it is up to us as the programmer to keep track of both our node of interest, our pos, and pos's parent. We must do that manually. And so I'll do that kind of explicitly here. I would hope that you would be able to figure out how to do that within the context of the prac. If you look at how pos changes as the while loop executes, and hopefully you will be able to identify a relationship between how pos changes and how pos's parent changes. If you're struggling with that, I would suggest you revise over how to traverse through a linked list, and how you would work with cur and prev. Yes, but I'm getting sidetracked here. So here I'm just going to explicitly set parent to point at the parent of pos, which in this case should be node B. Yes, node B is, here you can see, node B is the parent of node C. Node C is in the left subtree of node B. So we are just going to go ahead and explicitly set that. We'll do parent equals mytree dot left. And now if we run this, parent, yes, parent points to B and pos points to C. So we are interested in changing C, but in order to do so, we need to know where its parent is, which in this case is node B. So, okay, now we need to create our node, which we would be inserting in the place of C. So let's just go ahead and create a new tree string. Tree string, we'll call it new node. What have I done here? Tree string new node equals new tree string. Why did that not capitalize? Equals new tree string, and we will give it some data to contain. Since it's replacing C, we can make it contain Charlie, and then we will set its left subtree to null and its right subtree to null. Okay, so this is going to be the new node which we hope to take the place of C. So we hope to replace C, here, the data field of this node, with Charlie, the data field of our new node, effectively. Okay, so now we'll go ahead, but we'll see that nothing is pointing to new node yet. Nothing is pointing to Charlie yet, because we have not actually linked it into our tree. And in order to link it in, we're going to make use of our replace methods, which we wrote as our answer to question 1. But if you remember earlier in the video, we discussed that pos has no way of knowing which node is its parent, and kind of in the same vein, it also has no way of knowing whether it's in the left subtree or the right subtree of its parent. As far as pos is concerned, it's effectively the root node of its own subtree, which it is actually. But anyway, so I hope you can see how pos has no way of knowing whether it is the parent's left subtree or the parent's right subtree, since it has no pointer to this, to its parent. So we are going to have to go and explicitly test for that. And we can do this quite simply, actually. We can just say if, and then, wow, if pos.getData is equal to parent dot left dot get data. That's because I didn't put a. There we go. Get data. Whoa. Why is that not? Wow, I don't know why this is, it's a capital D, that's why. Okay, so here we are just comparing the data field of pos against the data field of parent's left subtree. So if the data field of pos is equivalent to the data field of parent's left subtree, that means that data, pos's data is our parent's left, pos is our parent's left subtree, essentially, if their data fields are equivalent. And this means that now we know that we need to replace the parent's left subtree if we want to replace pos. So here we would do parent dot replace left with new node. And so what this would accomplish is it replaces parent's left subtree with new node, if indeed pos is pointing to parent's left subtree. So this means that if this if statement is not true, so if we do else, that means we need to replace the right subtree. So we will do parent dot replace right with new node. And so this will be able to determine whether pos is in parent's left or right subtree, and then it will replace either the left or the right subtree accordingly. And it's going to put new node in place of pos. So I hope you can see how that works. And the reason, sorry, let's run that. And now we'll see that instead of C, we have Charlie here in B's left subtree. In parent's left subtree, we have Charlie. And similarly, we could make this, if we made pos point to parent's right subtree here, dot left dot right, then we should see that Charlie will take the place of D instead. I would hope. Let's see. Yes. So now that we see that parent's right subtree has been replaced by Charlie, if we set it to the right subtree, mytree.left and then mytree.left.right. Okay. So now the reason that this is useful is because we can take advantage of a key fact about trees, and that is that every node which makes up a tree is in its own right a tree. So instead of replacing this node with just a node, we could in fact replace this node with an entire tree. And to illustrate that, I will just go ahead and kind of manually build a tree. So if we do tree string, we can call this new left equals new tree string. Does it need those? Oh, I must give it some arguments. Okay, so in the left subtree of this new tree that we're going to be adding, we can put, what can we put? Yes, let's put yes. And then we'll set these subtrees, the left subtree of this node to be null, the right subtree to be null, and this to be a capital. And then we'll just go ahead and make another one for the right subtree. Tree string new right equals new tree string. Don't know why these don't like capitalizing for me. And in here we can put indeed, and we'll set these left and right subtrees to null and null. Okay, and then for new node, we can construct this tree as having its left subtree as new left and its right subtree as new right. Okay, so now instead of replacing pos with just one node, we're going to replace pos with this entire tree. And you can see that each subtree of this entire tree is in fact a tree. It's a tree string, and that's why this works. And yes, I hope you can see why that would be useful. So when we run this, hopefully we'll see instead of D, instead of parent's right subnode subtree being D, we will see this entire new node, which is in fact a tree containing Charlie and then in its left subtree we'll see yes, and in its right subtree we'll see indeed. So if we run that, then we'll see that here, so it's a little bit unclear, but so in the right subtree of B, so parent is pointing to B, so in the right subtree we have Charlie now, and it is in fact an entire tree containing a left subtree which contains yes and a right subtree which contains indeed. And so I hope you can see how this would apply to Prac 5. I hope this was clear. I'm not very good at this kind of thing, and I hope this didn't take too long. But yes, so like I said, I feel that it's fair that you ask you to submit by 11 p.m. tonight. Please do try to submit by 11 p.m. because load shedding is scheduled for 11:30. And please do get in contact with me if this is a problem for you. If you have a legitimate reason for not being able to do the work, then we can talk about it. But yes, I really hope this helps. Please forgive me. I'm terribly, terribly sorry about this. I will make sure to be more prepared for pracs in the future. But yes, like I said, there shouldn't be too much work to implement. And I hope you can see how this is vastly, vastly different to what I told you to do. Anyway, good luck. Yep, that's it from me.